Last day, we looked at gravitational, or I like to think of it as cosmic potential energy. We ran into some problems. We said, first of all, we can't just use MGH in outer space because little g is changing. So we went to another way to think about work and energy as the area underneath the force versus distance graph. Then I have to be honest, Danielle, I did a little hocus pocus magic. I waved my hands. I said, well, I can calculate it by multiplying these two together. That it gives us the right answer, sort of. But I got to be honest, mathematically, I'm breaking some rules there. If you want, it's not quite a true mathematical statement. But we got to this. We said that gravitational potential energy is equal to big G, big M, little m over R. Now, force is big G, big M, little m over R squared. Oh, but gravitational potential energy is also negative. Why negative? For calculus students, it's negative because if you take the derivative of this with respect to R, you'll get force. Force is the derivative of work. For the rest of us, we said, well, we had to define zero somewhere, and defining zero energy as the surface of the Earth would both be egocentric, but also bad physics, because if you're sitting on the surface of the Earth and suddenly the Earth underneath you vanishes, you can fall, which means you must have had some energy. We said, where is zero energy going to be? The phrase we used was relative to zero at infinity. We said if you were all the way out, infinitely away at the edge of the universe, that's where you would have no potential energy. And the reason you would have no potential energy is there was no gravity acting on you, which meant if you shut your rocket engine off, you would not fall. You would just stay there. And if you wouldn't fall, how much energy do you have? Zero. Now, to get there, Lorenzo, we said you would have to burn rocket fuel. You would have to do work. You would have to add energy to get to zero, which means you're starting out with less energy than zero. What numbers are less than zero? Negatives. Okay? If you don't really wrap your brain around that, just make sure you use negative big G, big M, little m over R for cosmic potential energy. And if you're supposed to get a positive answer, it will take care of itself because you'll probably have a minus minus, which is a plus, and it will be okay. We did a question where we used conservation of energy. We figured out an asteroid collision speed. I'll mess with your minds next class on Wednesday. And then we started calculating how much work. And we found, no pun intended, these took a lot of work. We couldn't use force times distance. We had to use change in potential plus change in kinetic. And we got right to here. So here's a little thought experiment. It says this. A missile is launched from the surface of the Earth, but Ben, to keep it as simple as possible, let's suppose that we fire and we burn all of the rocket fuel instantly. So 3, 2, 1, launch. We hit full speed, let's say 1/100th of a second after we fire the engines, and we're going to coast the rest of the way. We're also going to ignore air resistance because that makes this yucky. So we fire all of our energy in a massive burst, and then we coast away from the Earth. As it rises, what happens to the kinetic energy and the orbital potential energy? Let's do kinetic energy first. I've told you for these chart questions, always answer them vertically, never answer them reading across. So as the rocket goes higher, if we've shut the engine off and we're coasting, what's going to happen to our speed? So what's going to happen to our kinetic energy? So I'm going to go no, no, yes, yes. What's going to happen to the potential energy, the gravitational potential energy? In fact, that's where the kinetic energy, because the energy's got to go somewhere. You want to know where most of the kinetic energy is going? It's going into increasing our potential energy. So yes, no, and the correct answer is clearly C. Is that okay? What we're going to ask next class is, what if we fire our engines and then shut them off and start to coast? What if we want to coast and reach the very, very edge of the universe? How fast do we need to leave the Earth at? We call that escape velocity. Should be called escape speed because it's technically a scalar, but in the industry it's called escape velocity. And we've done that. When the astronauts went to the moon, they achieved escape velocity from the Earth. They coasted most of the way to the moon. They got out of Earth's gravitational field. Example 4. I like example 4. I like example 4. I like example 4. Example 4 is a nice question. A satellite is placed in a stable orbit with a speed of 4,200 meters per second. A. Hannah, what does A want me to find? Did you say orbit? My first thought when I see that is to maybe say gravity is what's pulling me in a circle. By the way, what's the second thing this is asking me to find, folks? Write small. I know I left you a whole page. Write small, because it takes a lot of work to find work. I wish that was a joke. It's not. It's just a lot of writing. Gravity is big G, big M, little m over r squared. And then FC is MAC. Hannah, which version of AC am I going to use? Did they give me or ask for period, or did they give me or ask for speed?
Neither.
Did they give me or ask for period, or did they ask? Sorry? Yes. MV squared over R. I'll use that one. Now, otherwise, I could have given you the orbital period. Okay. I think I said to you there's 4 things in orbits. Orbital radius, orbital speed, orbital period, and altitude, which is radius minus radius of the planet. If I give you any one of those, you can find the other 3. If we're in orbit, gravity is what's pulling me in a circle. So, what's going to cancel here? Little m? Does an r cancel here? Does an r always cancel? No, you have to be very, very careful. The m4 pi squared r over t squared, there the r won't cancel. Hannah, what am I trying to find? Where is the r in this question? Ugh. Oh, wait. Let's multiply it to the top, and let's move the v squared to the bottom. If I hear you correctly, Hannah, you're telling me the orbital radius is going to be big G, big M over v squared. And I don't think I need to square root or anything. I've got the r by itself. So it's going to be 6.67 times 10 to the negative 11. Big M, mass of the planet. Are we on the Earth or around the Earth? I would say this. I didn't technically say the Earth in this question. Unless I say a different planet, assume we're on the Earth. Now, in your homework or on a test, I might take you to the moon because why not? So just make sure you read the question carefully. If we're orbiting around the moon, make sure you use the mass of the moon. But this one is going to be 5.98 times 10 to the 24th. And V is 4,200 squared. And again, all of you want to practice these because the calculator work is pretty heavy duty. So you want to make sure you're getting the same thing as me. I got 22,611,451.25. I'm going to probably write down all of the non-decimals in case I'm going to use this. So I'm going to go 22,611,451, 22,6, what was it? 11451. Mr. Dueck, is that right? And then, Gabe, I'll give it to, let's say, 3 sig figs, 2.26 times 10 to the 1, 2, 3, 4, 5, 6, 7 meters. Do I need to add the radius of the Earth to that to get the orbital radius? No, because this wasn't an altitude. This was a radius, which means it's already being measured from the center of the Earth. Okay. Maggie, what's B want me to find? Oh, that's easy. Because I can just go work equals, don't write this down, force times distance, can't I? Why can't I? Oh, the force is changing. Well, it would also be the area underneath the force versus distance graph if they'd given me that, but they didn't. What's my third definition of work, what we called work energy theorem? And sadly, I don't think any of these are zero. Now we're going to be doing some fairly heavy-duty calculator work. I would encourage you to do these separately. What do you want to find first? The change in potential or the change in kinetic? I don't care. Pick. Potential, potentially? Okay. So change in potential is going to... What's change in anything? So this is obviously going to be mgh final, don't write this down, minus mgh initial, right? That's easy. Why can't I go mgh? We're going cosmic here. So it's going to be negative big G, big M, little m, over R final minus negative big G, big M, little m, over R initial. Now, Maggie, I do want a positive answer because it will take work. And at first you might think, Mr. Dueck, you're going to get a negative answer. But what's a minus? Minus the same as. And not only that, when I calculate this positive value, it will be bigger than this negative value. And so we will get an overall positive answer. Okay. This is going to be negative 6.67. I don't know if I can fit this in one line. I got to go to another line. 6.67 times 10 to the negative 11. 5.98 times 10 to the 24th. What was the mass of the satellite? I've scrolled down. Oh, no, it cancels, right? There's an M in everything here, right? Oh, there isn't an M in the potential. You know what? It shouldn't cancel because it would take more rocket fuel to put the space shuttle up there than it would to put a tiny little cube satellite up there. 1,800 divided by R final 2261145. I don't need to add the radius of the Earth to that because it is an orbit. I'm going to use my answer button. And then I have a plus same thing times same thing times same thing divided by my initial radius, I think, is the surface of the Earth. 6.38 times 10 to the 6th. And Lorenzo, we decided to do it this way because this is a lot of typing. And then what I said is, don't do this in one step. Do each term one at a time. So I'm now going to go negative 6.67 times 10 to the negative 11 times 5.98 times 10 to the 24th times 1,800 divided by, answer button. And I get negative 3.1752 times 10 to the 10th. And I'll write it all down. Plus. And Lorenzo, what we said last day that we're going to do is we're going to backspace and edit on our calculators because we noticed most of these numbers aren't going to change. I backspace to the very front of my calculator so I can delete the negative. And then I'm going to delete the answer button and replace it with 6.38 times 10 to the 6th. Now, those of you that have big G built into your calculator, you're probably going to notice on the 4th or 5th sig fig, our answers will be different. But most of us would get 1.125327273 times 10 to the 11th. Or not. Yeah. I'll go to the 3. 1.1253. 1.1253 times 10 to the 11th. I think I told you that when we're talking about space orbits, usually we're in the 10 to the 10th, 10 to the 11th range. If you're talking around the Earth, if you're talking around the Moon, you'll often be in the 10 to the 9th, 10 to the 10th range because the Moon has a weaker gravitational field strength. Let's add these together. So it's going to be this plus negative 3.1752 times 10 to the 10th. And I get 8.078. I'm going to carry extra sig figs here. 8.0781 times 10 to the 10th. And that's potential energy, joules. Whew, are we done? We got more? Oh. All right, change in kinetic, you say. Maggie, what's changing anything? So this is going to be a half mv final squared minus a half mv initial squared. Or any of these, 0. What did we decide? Where did we decide we are launching from last day? Do you remember, Maggie? Where did I say we were going to decide we were launching from to make the math easy? North Pole. Superman's Fortress of Solitude, I think, is what I made the dumb joke. And that's to make the math easy. Now, in real life, if you're not launching from the North Pole, you do have some sideways kinetic energy because you're attached to the Earth, which is moving. In fact, the closer to the equator you can launch from, the better. That's why the U.S. built their Kennedy Space Center in Florida. But to make our math easy, we're just going to assume we're launching from the North Pole. 0.5, 1800, 4200 squared. Now, if I hadn't given you the speed, I could have given you the orbital radius, and you'd have to figure out the orbital speed. Gravity is what's pulling me in a circle. And I get 1.5876 times 10 to the 10th. So my final answer, work. It's going to be 8.0781 times 10 to the 10th. There's the change potential. Plus 1.5876 times 10 to the 10th. 8.0781 times 10 to the 10th. What'd you get? And now I'll round off. Hannah, I'm going to round off to the third sig fig right there. Is that 6 going to stay a 6 or become a 7? And so I'm going to write 9.67 times 10 to the 10th. Because I only round off once unless I'm bumping 9s into 0s. Then that carries through. Okay. What's your homework? I apologize. I need to give you lots of practice on this, both because it's a tricky concept, but also I want you to just get fast at typing this and find your shortcuts. So, sorry, but here it comes. Here's what I gave my black A's. By the way, lesson 5, black holes are attractive. Just saying, they are. It's going to be easier. I think I told you folks you could skip number 1, didn't I? So I'll say you can skip number 1, I guess. You can skip 5 and 6. Now, by the way, if you look at number 4, it says find the potential energy relative to 0 at infinity. In other words, that's their code for saying please make sure you use cosmic potential energy. 7, 8, 9. Sorry, skip 8. I'm sorry. 7, 9, 10. 11 is good. You can skip 12. 13, 14, 15. Okay.